The Irish Sea lies still, draped in fog, as if time itself refuses to move across its waters. For centuries, these shores, Irish and English, have stood opposite one another, shaped by stories of conquest, rebellion, kinship, and estrangement. But beneath the politics, beneath the centuries of division, there's something deeper, something older, something carved not into stone, but into blood. What if the story isn't what you were taught in school? What if the Irish and English, so often cast as opposites, are more genetically alike than most cousins across Europe? And what if the real difference isn't in who they are, but in how history has remembered them? Scientists once hoped DNA would draw neat lines, borders of ancestry, cut in genetic ink. Instead, it has only revealed gradients, a whispering fog of shared genes, overlapping identities, and a past that doesn't fit into simple categories like Celtic or Anglo-Saxon. The myths of pure bloodlines and ancient separateness are seductive, but wrong. And as we now hold the power to sequence entire genomes, one truth is becoming unavoidable. Ireland and England are branches of the same ancient tree. The leaves may flutter in different winds, but their roots are tangled. In this journey, we will uncover that tangled story, from prehistoric migrations that shaped both lands, to the echo of Viking raids, to the quiet endurance of maternal DNA, and the painful legacies of empire and exile. Each chapter will unravel a new layer of identity, some shared, some diverged, all real. But first, we begin not with war or politics, but with blood, the silent record-keeper of human history. Long before there was an Ireland, before there was an England, before anyone ever spoke the words Gaelic, or Anglo-Saxon, or even Celtic, there were only people, small bands of hunter-gatherers, their footprints pressed into cold mud at the edge of melting glaciers. And as the Ice Age loosened its grip on Europe, they moved north, chasing the game, chasing survival, into the empty lands that would one day become the British Isles. But here's the twist. Those first humans? They weren't Irish. They weren't English. They were everyone's ancestors. When scientists extract DNA from skeletons dated over 9,000 years ago, found in caves, peat bogs, riverbanks, they find something astonishing. The Mesolithic hunter-gatherers, who colonized both islands after the ice retreated, left their mark in both modern Irish and English genomes. Not in myths, in measurable base pairs. And then came the first real disruption, the farmers. Around 4000 BCE, waves of Neolithic migrants swept across Europe from what is now Turkey and the Near East. They didn't just bring crops and livestock, they brought genes. They intermarried with the native hunter-gatherers, slowly reshaping the very biology of the islands. These weren't warriors. These were agricultural pioneers, and yet they changed the genetic structure of Ireland and Britain forever. But here's what most people miss. Those Neolithic farmers didn't stop at Stonehenge or the Irish Midlands. Their descendants live on today in both populations, with slight differences in proportion, but a massive shared origin. We carry their legacy in how we digest food, in our skin tone, even in the shape of our bones. So if you're watching this and your family roots trace back to either Ireland or England, your ancestors may have knelt in the same field, planting the same wheat, thousands of years before anyone argued over flags or borders. And then came the most important shift of all. Around 2500 BCE, another group began pouring into Europe from the east, from the vast Pontic-Caspian steppe, bringing horses, metal, and a language that would eventually evolve into every modern Celtic and Germanic tongue. Their DNA, rich in what scientists call steppe ancestry, exploded across the British Isles. And this is where we begin to see the birth of something resembling Irish and English genetic identity, not because of war, but because of a slow population turnover so total that it changed the dominant male lineage in both lands. The Y-DNA haplogroup R1b, especially the branch called R1b, L21, surged in frequency, especially in the West, what we now call Ireland, Wales, and Western Scotland. Imagine that, a single migration wave, over 4,000 years ago, still defining the majority of Irish male lineages today. A genetic echo strong enough to drown out nearly everything that came before it. But what's fascinating is that the same R1b lineage also dominates England. Not identically, Not at the same frequency, but unmistakably there. In your veins, in your father's father's line. The same route, branching in different directions. How often do we hear about ancient migrations in school? How often are we told that our ancestors rode in chariots, carried bronze swords, and shaped entire populations not with ideology, but with children? It's easy to think of history in terms of kings and empires, but genetics tells a quieter, older story, one that began before any nation existed, before the idea of Irish or English was even possible. And now you have to ask yourself, if we all began at the same place, how did we end up seeing ourselves as so different? Something strange happened around 2500 BCE, and the human story in Ireland and Britain changed forever. It didn't happen overnight. There was no grand battle, no sudden collapse. But across the ancient skies of Western Europe, a quiet revolution was unfolding, one that would rewrite the genetic future of the islands and define what we now call Celtic. For thousands of years, Neolithic farming cultures had thrived in Ireland and Britain, building tombs, raising cattle, carving stone monuments aligned with the stars. Then, from far beyond the Black Sea, came a people utterly unlike anything these early farmers had ever seen. Tall, nomadic, fierce. These were the steppe pastoralists. They rode in on horseback with strange burial rites and unfamiliar metal tools, bringing not only bronze, but a bloodline so potent, it would nearly erase the genetic legacy of the people who came before them. But how do we know this? Because when geneticists began analyzing the remains of those who lived before and after this moment, they discovered something shocking, a near-total population replacement. In Ireland, as much as 90% of the male lineage was turned over in just a few centuries, almost like the old Ireland vanished. This wasn't just migration, it was transformation. And yet, this new DNA wasn't just foreign. It blended with the land. It adapted. And in time, it became Irish. This was the moment the roots of what we now call the Celtic genome were planted. Not in poetry or myth, but in chromosomal signatures. The Y-DNA haplogroup R1b L21, now carried by the overwhelming majority of Irish men, didn't start in Ireland. But Ireland made it its own. And that begs the question, what does it mean to be native? If your ancestors arrived 4,500 years ago and replaced nearly everyone before them, are you a settler? Or are you, over time, transformed by the soil, the weather, the language, the silence of the bogs? While much of Europe saw this migration from the steppe as just one layer among many, Ireland did something unusual. It absorbed it almost completely. The pre-Bronze Age Irish genome, faint traces, shadows. But the Bronze Age? It's everywhere. In the bones buried under ancient ring forts, in the blood of modern schoolchildren, in the very structure of rural surnames. But what about Britain? Yes, the steppe ancestry arrived there too, almost as powerfully. But Britain would face wave after wave of new arrivals over the next 3,000 years. Romans, Saxons, Vikings, Normans. Ireland, by contrast, remained relatively untouched for centuries. It became the time capsule. So while both islands drank from the same genetic river in the Bronze Age, it was Ireland that held the water still. That preserved it. And what about culture? Many people think of Celtic identity as a linguistic or artistic tradition. But what if it's also a genetic memory? The same DNA that came with Bronze Age migrants carried with it the seeds of Indo-European languages. The rise of Celtic speech, of warrior aristocracies, of druidic elites. These weren't born in the mists of Irish mythology. They came with the people. So when you think of Celtic heritage, ask yourself, are you thinking of myths and festivals? Or are you thinking of ancient DNA that still shapes how your cells work today? Science now allows us to pull those ancient voices from the soil and sequence their stories. And what they tell us is this: the real beginning of what we recognize as Irish DNA wasn't born in Ireland. It arrived, it conquered, and it stayed. By the time the Roman legions withdrew from Britain in the early 400s AD, the land they left behind was vulnerable and waiting. What followed wasn't peace. It was a storm. From across the North Sea came ships, low, fast, filled with warriors who didn't speak Latin or Celtic. They were the Angles, the Saxons, and the Jutes. And they weren't here to raid. They came to stay. But here's where history gets murky, and DNA begins to speak. For generations, the dominant myth was that the Anglo-Saxons wiped out the native Britons, driving them west into Wales and Cornwall. But when geneticists sequenced ancient Anglo-Saxon skeletons and compared them to modern English people, the results were complex. On average, about 38% of English ancestry today comes from those early Anglo-Saxon settlers. But it wasn't evenly spread. In East Anglia, it's higher. In Devon or Cumbria, it's far lower. What does that mean? This wasn't mass extermination. It was intermarriage, assimilation, and slow transformation. And now comes the real twist. This massive infusion of continental European DNA is something Ireland almost entirely missed. The Saxon genes barely touched the Irish genome. While England shifted on a cultural and genetic axis, Ireland watched from across the sea, its Bronze Age foundations still largely intact. So, ask yourself, how much of what we call English today is actually Germanic in origin? Because genetically, Saxon men brought new Y chromosome lineages into Britain. Haplogroups like I1 and R1a, uncommon in the Celtic West, began to rise in the east and southeast. Names changed. Languages changed. But under the microscope, it was still a fusion, not a replacement. Then came the next wave. The Vikings. From the late 700s onward, longships once again carved paths through British waters. Unlike the Saxons, the Norse were not content to settle farmland. They built towns, took slaves, established kingdoms. The Danelaw in eastern England became a real political entity. York became Jorvik, and the DNA of the Danes slipped into English bloodlines. How much? Roughly 6 to 10% in most of England. But once again, not evenly. The Viking legacy left a deeper mark in certain regions, especially where they settled in numbers. Places where Norse words still linger in dialects, where surnames still whisper of fjords and frost. But Ireland? Here's where things flip. In coastal Irish towns, like Dublin, Waterford, and Limerick, Norse ancestry can reach up to 16%. And this time, it came mostly from Norwegians, not Danes. It's one of the few moments in history where Ireland took in more Norse DNA than England. That's the paradox. England, transformed by Saxons and Danes. Ireland, less touched by Saxons but deeply imprinted by Norse settlers, especially in pockets. And yet, despite centuries of invasion and assimilation, the English genome didn't become unrecognizable. Instead, it became layered like sediment. Underneath the Germanic and Scandinavian contributions, the original Bronze Age foundation still pulses. So if you think of English ancestry as a pie chart, it's not divided in neat slices. It's a swirling blend. Bronze Age, Saxon, Viking, Norman. Each phase left something behind, but none completely erased what came before. And what's even more surprising, despite all of this, England today still shares more DNA with Ireland than with France or Germany. Even with the Saxon storm and Norse shadow, the base remains native to the Isles. So next time you hear someone talk about pure English blood, or claim that the Saxons replaced the Celts, ask them this: have you seen the DNA? Because England didn't become someone new. It became many people at once. By the end of the Viking Age, the British Isles had already seen centuries of change. But the next chapter would come not on the tide of longships, but from across the English Channel. The Normans were coming, and they carried with them a new kind of conquest, one that reshaped not only politics and power, but also the very strands of DNA running through both England and Ireland. The year was 1066. William, Duke of Normandy, descended of Vikings who had settled in northern France, landed on English soil, and changed history in a single battle. Hastings. One moment, one king, one arrow. But what came after was far more transformative than any crown. The Normans weren't just warriors. They were administrators, aristocrats, and builders. And they came with wives, retainers, and entire networks of bloodlines, shaped by centuries of life in continental Europe. Their DNA was part Viking, part Frankish, part Breton, a melting pot of medieval northwest France. Over the next few generations, they embedded themselves into the English elite. They didn't replace the population, but they did seed it. In modern English genomes, small but detectable traces of Norman ancestry still remain, often subtle, often overshadowed by the earlier Anglo-Saxon and Viking layers. But real. Now here's where it gets more tangled. Because just over a century later, in 1170, the Normans came again, this time to Ireland. But the dynamic was different. Led by the likes of Richard de Clare, Strongbow, they arrived not as invaders, but at the invitation of an Irish king. That invitation turned into centuries of domination. But what did it mean for Irish DNA? Unlike the Anglo-Saxons or Vikings, the Norman impact in Ireland was more social than demographic. There was intermarriage, yes, but no mass migration. Yet genetic studies today show a quiet footprint, a northwest French-like component in Irish DNA that wasn't there before the 12th century. In Eastern Ireland, especially around Leinster and the Pale, this Norman imprint lingers. Not overwhelming, but undeniable. Proof that even small elite populations can leave a genetic trace if they hold power long enough. But now, let's fast forward 500 years. Because the most profound genetic transformation in Ireland after the Bronze Age didn't come from the Normans. It came from Britain again, the Ulster Plantation. In the early 1600s, following the 9 Years' War and the flight of the Gaelic Earls, England launched a calculated colonization of Northern Ireland. Thousands of settlers, mostly Lowland Scots and some English Protestants, were granted confiscated Irish land. This wasn't a raid. This was a blueprint. And this time, the demographic shift was massive. DNA from modern Northern Irish populations shows clear evidence of British input, especially Y-DNA haplogroups more common in Scotland and Northern England. In places like Antrim and Down, the genetic signature of the plantation is still visible centuries later. So what's the legacy? In England, the Norman genetic input is light, but widespread, an echo of power. In Ireland, the Norman thread is localized and elite, but the Ulster Plantation left a deeper, more lasting population-level imprint. It reshaped the North, creating one of the few places in Ireland where British and Irish genomes now truly blend. And yet, there's a strange poetry to this. Because while the politics of colonization carved borders in blood, the DNA tells a quieter truth. Over time, people mixed. Not completely, not equally, but inevitably. So when you look at a map of genetic clusters in modern Ireland, you'll still see distinct regional groups. But in Ulster, you'll see the blend, the bridge, the tension, and the truth. So what do we make of it? Is identity a straight line, or a woven thread? In the ancient code of life, there's one strand that doesn't lie. The Y chromosome, passed from father to son, is a direct record of every male ancestor you've ever had. And when scientists look at this tiny sliver of DNA across Ireland and England, they find a tale of two islands with very different histories written in male blood. Let's start with Ireland. Today, nearly 85% of Irish men carry a single paternal lineage, R1b, more specifically a subbranch called R1b, L21. This isn't just a statistic. It's one of the highest concentrations of a single Y-DNA haplogroup in the world. In parts of Western Ireland, the numbers go even higher. It's as if the ancient Celtic male lineages held their ground and refused to budge. But why did this happen? Because after the Bronze Age, Ireland became a genetic time capsule. There were fewer invasions, fewer replacements. And when newcomers did arrive, they rarely came in numbers large enough to shift the deep paternal line. Now cross the water to England, and the story changes entirely. There, R1b is still dominant, but not in the same way. Nationally, it ranges from 60% to as low as 45% in the East. In its place, other lineages rise, particularly I1 and R1a. These aren't Celtic. These are Germanic and Scandinavian markers, carried by Anglo-Saxon and Viking men who reshaped the English gene pool. Let's break that down. I1 is often called the Viking haplogroup. It's most common in Sweden and Norway, and in England, it reaches 10–15%, especially in the east and southeast. That's no coincidence. That's where the Saxons landed. That's where the Danelaw ruled. That's where male ancestry took a sharp turn toward the continent. Then there's R1a, another outsider. This haplogroup is linked to Eastern European steppe peoples and Viking groups, especially those moving westward. In England, it sits around 4 to 5%. In Ireland, barely 2.5%. What does this tell us? It tells us that while both countries experienced external influences, England absorbed far more male-mediated migration. The invasions weren't just about armies. They were about generations of sons born with new chromosomes. And that raises a deeper question. Where were the women? Because if the male lineages shifted so dramatically in England, but the maternal DNA, as we'll see later, stayed consistent, then the answer is uncomfortable. Men arrived, but women didn't. These were not balanced migrations. They were male-dominated, reshaping the Y-DNA landscape without touching the maternal one. Now, zoom in closer on our 1B itself. Even within this group, there's a divide. Ireland's R1b is overwhelmingly L21, the so-called Atlantic Celtic branch. England, meanwhile, shows a higher percentage of U106, a branch tied to Germanic and Saxon ancestry. So even when both men carry R1b, the story their DNA tells is different. It's not just about the name. It's about the path that lineage took across history. Imagine two men, one Irish, one English. Both might test R1b, but one's ancestors may have crossed the Alps as Bronze Age Celts. The others may have come from the North Sea as a Saxon warrior. Same route, different journey. And here's where it gets even more fascinating. These lineages, these silent Y chromosome signatures, often show up in places you wouldn't expect. In surnames, in medieval land records, in tiny rural villages where a single paternal line has dominated for centuries. Entire family trees growing from a single Bronze Age seed, unbroken for over 4,000 years. So the next time someone tells you they're Irish or English on their father's side, pause and consider what that really means. Because in the end, the Y chromosome doesn't just carry genes. It carries legacy. Through all the wars, all the migrations, all the kingdoms that have risen and collapsed, there's one thread that held quietly through it all. One legacy untouched by conquest or crown. It's found not in the story of kings, but in the line of mothers. This is the story written in mitochondrial DNA, passed down exclusively from mother to child, generation after generation, like an unbroken whisper through time. And when we look at it across Ireland and England, something extraordinary happens. The chaos disappears. Because while Y-DNA tells us of invaders, battles, and dramatic turnover, mitochondrial DNA tells us something else entirely: continuity. Despite waves of male-led migrations, the maternal gene pool across the British Isles has remained surprisingly stable for thousands of years. How can that be? Think about it. Most of history's migrations, Saxons, Vikings, Normans, even the Ulster planters, were male-dominated. Soldiers, merchants, settlers. But they didn't always bring women with them. They arrived married, or took local wives. And so, while the paternal lines were replaced, the mothers stayed. In both Ireland and England, mtDNA haplogroup H is dominant. Not just common, dominant. This lineage, which traces back to Ice Age Europe, runs strong in the West. In Ireland, in England, in Wales. You'll also find U, K, J, T, all part of that ancient maternal mosaic that predates recorded history. And here's the kicker. There's no sharp divide between the two populations. Not here. In fact, mtDNA across Ireland and Britain is so similar, it's nearly indistinguishable. The same genetic signatures appear across counties and coasts, defying modern political boundaries. But what does that actually mean? It means that while kings waged wars and borders shifted, women held the genetic line. They raised children, passed on language, culture, and mitochondria, quietly preserving a piece of the past that swords could not sever. Now here's where it gets personal. You might know your surname, maybe even your Y-DNA haplogroup. But do you know your mitochondrial lineage? Do you know the name of your mother's mother's mother, 10 generations back? Probably not, because society rarely celebrates maternal ancestry. But in genetic terms, it's just as powerful, sometimes more so. And that's what makes this so fascinating. The maternal story is not one of replacement, it's one of survival. Whereas male haplogroups show fragmentation, one branch dominant in Ireland, others in England, mtDNA doesn't play favorites. It tells a shared story, a deeper, quieter ancestry that has been passed down in kitchens, in lullabies, in the silent bonds between generations of women. And yet, it's largely invisible. You won't hear about mtDNA in history books. There are no monuments built to mitochondrial inheritance. But science sees it now clearly. It connects a grandmother in Galway to one in Gloucestershire without missing a beat. Even the regional variations are soft. In Britain, some haplogroups show slight north-south gradients. In Ireland, a few subclusters reflect local founder effects. But overall, it's one great continuum, a maternal river flowing beneath the island's rugged skin. So if you've ever wondered how people stay connected despite war, conquest, and displacement, here's your answer. Not through armies, but through mothers. The same mothers who stood at doorways as sons went to war, who taught their children the old words, even when new rulers outlawed them, who buried their dead and carried memory forward when the world refused to. They didn't lead invasions, but they shaped nations. If you zoom in close, too close, all you see are differences. A haplogroup here, a mutation there. But what happens when you zoom out? When you take the full human genome, all 3.2 billion base pairs, and lay them side by side, that's where the real story of Irish and English DNA begins to blur. Because while history loves division, tribes, borders, empires, genetics is not so easily fooled. When researchers ran principal component analyses, clustering thousands of people from across the British Isles, they expected neat categories. Instead, they saw a gradient, a soft continuum of DNA, stretching from west to east like mist rolling over the land. No hard breaks. No clean cuts. Just subtle shifts. You'd expect Ireland to form a distant outlier from England, separated by centuries of cultural tension. But it doesn't. In fact, genetically, Irish and English people sit closer to each other than to almost any other population in Europe. Even the PCA plots don't place them in opposing corners. They overlap, brush shoulders, blend. And this isn't just abstract science. It's concrete, measurable. Take FST values, the genetic distance between populations. Between Ireland and England, it's 0.0013. That's not small. That's microscopic. For context, the distance between the English and Spanish is 5 to 10 times greater. So what does that really mean? It means that if you were to take a random person from Dublin and one from Liverpool, their genomes would be almost indistinguishable. Not just similar, virtually interchangeable, especially when compared to someone from Germany, France, or Scandinavia. And yet, we don't feel the same. Why? Because genes don't carry flags. DNA doesn't recognize the Irish Sea, or the border of Ulster, or the ghost lines left behind by colonial maps. It only sees inheritance, shared ancestry, ancient migrations, common roots. But that doesn't mean there's no structure. Zoom in just enough, and patterns begin to emerge. The Irish DNA Atlas Project found regional clusters tied to historic provinces: Munster, Connacht, Ulster. In Britain, the people of the British Isles study uncovered clusters in Cornwall, Yorkshire, Orkney. Even within Ireland, Ulster stands apart, genetically tethered to Scotland and northwest England through centuries of plantation history. And yet even there, the differences are of degree, not kind. What's remarkable is how homogeneous Ireland is compared to Britain. In genetic terms, an Irish person from Cork and one from Mayo may be more similar to each other than two English people from Yorkshire and Kent. That's the power of isolation and preservation. Meanwhile, Britain's patchwork reflects its history, a land of crossings, minglings, layers. And here's where the real insight lands. Despite all this complexity, the majority of both English and Irish ancestry comes from the same deep roots: the post-Ice Age hunter-gatherers, the Neolithic farmers, the Bronze Age herders from the steppe. So if 95% of the genetic story is shared, why do we focus so much on the 5% that's different? Is it politics? Pride? The illusion that difference defines us more than connection? Because genome-wide, the evidence is overwhelming. English and Irish DNA are not enemies. They're not strangers. They are variations on a theme, echoes of the same song, played in slightly different keys. And what makes this even more powerful is the human angle. Tens of thousands of people from both nations have now taken commercial DNA tests. Many discover Irish ancestry when they expected none. Others find English lines running deep through their family tree. Cousins across borders. Shared segments. forgotten connections resurfacing after centuries of silence. It's not just science, it's personal. So ask yourself, if we share so much, why do we cling so tightly to the idea that we are so different? They may speak with different accents, carry different flags, remember different histories, but deep beneath the skin, Irish and English people share far more than they think, including the traits written directly into their biology. Let's start with something deceptively simple: eye color. Blue and green eyes dominate in both populations, a trait inherited from ancient European ancestors who settled these islands after the last ice age. That genetic blueprint? It's still at work today, every time a baby opens their eyes in Dublin or Derby. But as we dig deeper, the similarities grow stranger and more serious. Take hemochromatosis, sometimes called the Celtic curse. It's a condition caused by a mutation in the HFE gene, leading to dangerous iron buildup in the body. Carriers often show no symptoms until it's too late. And here's the shocking part. Ireland has the highest rate in the world. About 1 in 83 Irish people are affected, with as many as 1 in 5 carrying the faulty gene. England follows closely behind. But why is this mutation so common? One theory suggests it once offered a survival advantage. In iron-poor diets, retaining more iron might have helped. But today, in a world of abundance, that same adaptation becomes a risk. What once saved lives now shortens them. Then there's cystic fibrosis, another inherited disease, with deep roots in northwestern Europe. Ireland again leads the world in incidence, with roughly 1 in 19 people carrying the CFG mutation. England's rates are lower, but still among the highest globally. And the pattern continues. Both populations have some of the highest frequencies of lactase persistence, the ability to digest milk into adulthood. A rare trait globally, but common here. It's a genetic echo of prehistoric dairy farming, when survival favored those who could drink from the herd. But perhaps the most visible shared trait? Red hair. The fiery gene, tied to mutations in the MC1R gene, reaches record levels in Ireland. About 10% of population has naturally red hair, and up to 40% carry the gene. In England, the number is lower, around 4% redheads, but still among the highest on Earth. And it's not just hair. This gene affects skin tone, freckling, and even pain sensitivity. So yes, the Celtic fringe is more than a myth. It's in the mirror. But what about where these populations differ? One major distinction lies in autoimmune disease rates. Ireland has some of the highest known rates of celiac disease, an immune reaction to gluten. Why? Because the genetic markers associated with it, HLA, DQ2 and DQ8, are disproportionately common in Irish DNA. England has high rates too, but Ireland stands at the peak. The same goes for multiple sclerosis, MS. Though the causes are complex, genetic, environmental, even linked to sunlight exposure, the rates in Ireland, Scotland, and northern England form a kind of MS belt through the northwest of Europe, a shared vulnerability wrapped in centuries of shared ancestry. Still, despite these patterns, the overall truth remains. Irish and English people are medically and genetically more alike than different. Doctors studying blood type frequencies, for instance, find that both populations are overwhelmingly type O and, another Northwest European signature. In contrast, type B, more common in Eastern Europe and Asia, is rare across both islands. So when it comes to genetics, how much is really unique? The differences we see, like disease risk or hair color, aren't from different genes. They're from different proportions of the same genes. Irish genomes lean slightly more Celtic. English ones show a bit more continental flavor. But the parts? Almost all shared. So next time someone tells you their ancestry makes them pure Irish or pure English, ask them, in what gene exactly? Because in the most fundamental sense, these two populations are built from the same ancient ingredients, just in different recipes. We've scanned chromosomes. We've traveled from the Ice Age to empires, from Bronze Age warriors to Saxon fields, Viking ports, and Norman castles. But now, as we arrive at the end of this journey, we face the most important question of all. What does DNA really tell us, and what does it leave unsaid? Because despite everything science has uncovered, there's a quiet limit to its reach. DNA is powerful. It can trace ancestry, map migrations, predict disease. But it cannot explain who you are. It can't tell you what stories you were raised with. It can't capture the lullabies your grandmother sang. It doesn't know what side of a border your parents grew up on, or what it felt like when they crossed it. When you look at the genome of an Irish person and an English person side by side, the differences are tiny, infinitesimal. They vanish compared to the massive overlap. Tens of thousands of shared variants, identical markers passed down from the same ancient sources. But that doesn't mean their lives were the same. History carved separation where biology didn't. Colonization, rebellion, migration, trauma, pride, all of it layered on top of a shared genetic foundation. And that's the paradox. Genetically, the Irish and English are cousins. In some cases, they are practically siblings. Yet for centuries, they've lived as though they were strangers. So the question is, what matters more? The blood that flows, or the stories we choose to tell? Some people will look at their DNA results and feel surprised, maybe even betrayed. They expected purity. They got complexity. They expected walls. They found bridges. But maybe that's exactly what they needed to see. Because identity isn't binary. It's not a code locked inside a double helix. It's alive, shaped by memory, geography, language, and legacy. Genetics can tell us that the average English genome is roughly 20% Irish in ancestry, and higher near the Irish Sea. It can show us that Viking blood lingers in both nations, in different places and different strengths. It can trace shared haplotypes, buried in chromosomes we'll never consciously feel. But it can't measure loyalty. It can't predict who you'll mourn, who you'll marry, what side of history your family stood on. DNA offers answers, yes, but it also hands us a mirror, forcing us to confront just how much we share with people we've been taught to view as other. And if this journey has revealed anything, it's this. There are no pure stories, only shared ones. So, whether your roots lie in rural Donegal or the hills of Yorkshire, whether your great-grandfather spoke Irish or clipped Oxbridge English, your genome doesn't know the difference. It only remembers migrations, unions, survival. It only carries what was passed down, without judgment, without pride, without shame. And maybe that's the greatest lesson of all. Because at the end of the double helix, past the data and the percentages, there's a truth waiting that none of us can ignore. We're not nearly as different as we think.